Well, I guess first of all, welcome. I'm here to talk to you about blockchain, right? So blockchain is a force for good and evil, right? I'm going to be talking about how to protect your data against hackers using blockchain technology, right? On the other hand, blockchain is underpinnings of Bitcoin, which is how you pay hackers ransom. So it's an interesting dynamic, right? So let me get started, okay? So why, why the in-database blockchain, right? And why, basically, the goal here is to talk about how to protect your data against hackers, right? And the sad reality is that we human beings are very highly vulnerable, right? We are either hackers, hopefully none of you in the audience are, okay? We could be rogue insiders, we could be compromised users, right? So we may have clicked on a bad email link and, and someone has stolen our credentials, or perhaps we'll be working for a corrupt government or agency or whatever, right? So what happens is, if you look at all the systems you run, there are lots and lots of security mechanisms, right? You sign on using your passwords, you have privileges, the data is encrypted, there are firewalls and so forth, right? But all these technologies are focused on keeping the bad guys out, right? But what happens when the bad actors have gained access to your data once they get past these external protection mechanisms, right? So that's what we're talking about, which is that blockchain is a way to address these unavoidable vulnerabilities, right? So the way to think about it is that it adds an additional layer of protection after the bad guys are broken through the perimeter, right? And the goal is to protect your data from being illicitly modified or deleted, right? And it uses standard technologies, cryptography, signatures, and so forth. Okay. So when I first talk about blockchain, two things come to mind, right? First, I think it's still hot technology, but I think people who tried it know that it's very hard to use. Okay? And here are some quotes on the web, right? And actually I like the last one. Overwhelming and frustrating to understand. Okay? And blockchain indeed is complicated, right? So my group does a variety of blockchain technologies, and we realize that blockchains require new applications, new development methodologies, chain code, new data management products, and hardest of all, new business practices, because it requires cooperation among many different entities to make things work. Okay? So these things just make them much, much harder. So one of the key motivations we did was to build blockchain into the database. Is that actually first I want to give the notes that in this talk I will be using the Oracle database as an example of how you can integrate a blockchain into a relational system, because Oracle is widely used in financial industries, right? And so the goal of this is really to incorporate blockchain technologies into the Oracle database such that it makes it easy for application developers to implement blockchain applications with minimal changes. That's the key thing, make it easy, right? And the goal, again, is to prevent illicit changes to data, right? And the data you want to protect are things like titles, right? Contracts, transactions, accounts, and so forth, right? This is the kind of data that you want to preserve. You need to keep for legal reasons, right? And must never be changed, right? So for instance, if you have a title to a house, right? I don't want someone to overwrite the title with somebody else, because then they've sort of taken your property, right? And so this is a data that can never be modified, but that can be deleted only when it's obsolete, okay? And obviously, this kind of data you don't want to have modified illicitly, because bad consequences can happen, right? And the last thing that's very interesting is that the way that Oracle has implemented blockchain is that it's not limited to just ledgers, right? Because conventional blockchain is what's called distributed shared ledgers, which is just ledgers, right? And so this inside the database, the blockchain can protect reference data also, right? So that's being very abstract, so I'll give you some concrete examples. Okay? First, it's not a live demo, it's a static demo. Okay? So here is what it looks like to create a table, right? So I connect it's a movie database, right, showing movie rentals and so forth. And I can first create a blockchain table. And that's the key thing. In red, that's a new keyword that I've introduced to SQL syntax that says that this particular relational table is a blockchain table, right? It has certain properties and so forth. Now, I can connect to it as a user and add some information saying, we sold 2 movies, to these people at such a date and so forth. Okay. Now that's the normal part, right? So the next part is interesting, which is that now suppose we're going and modify the row, right? And the interesting thing is, first of all, we're connecting a sysdba. Sysdba is the most powerful user in a database. That's your super database administrator, the way I think about it. Okay? And then this sysdba person tries to update the record. Just say, hey, I'm going to change the price at which it was sold to something else. Change it from 3 value to 10, right? And notice how it gives an error. Say, operation is not allowed. Okay? So you can see that within this database, blockchain tables are protected against even the most powerful users. Okay? So that's an interesting property, right? All right. So I'm going to now talk about a little bit how this is done, right? So a blockchain table basically is an immutable table, right, that automatically changes new rows to existing rows cryptographically. Okay? Hence the blockchain, right? The way it works is that when I insert a new row, we compute a cryptographic digest on that row, right, plus the cryptographic digest of the previous row. So like this row plus digest of the previous row. And so you can see how each row is related to its previous row, and the whole thing forms a chain. And so the key observation, or key property about this is that if you try to modify an existing data, right, you change the data, that means change the cryptographic digest, that means the successive rows will no longer match, right? So that's how you can detect tampering, okay? Now, within this structure, you can add new rows, new data, but you cannot change existing data. Because again, the data would not match anymore, right? The checksums wouldn't match, and so forth, okay? And so this is great, right? So going back to motivations, right? So notice how this does not prevent you from looking at the data, right? And so the whole idea is to prevent, to limit the damage from what I call unavoidable vulnerabilities, okay? So the goal is not to prevent the hacker from looking at your data, because that's something else, right? But the goal is, even the hacker can look at your data, they cannot change your data, right? The way to think about it is following, right? If my bank account records, my statements got released on the internet, that's not good. That's not good, right? But that's far better than if my bank records were modified by somebody to steal money, right? So this technology is meant to prevent someone from stealing the money, not for prevent someone from looking at your money. To prevent someone from looking at your money, you should use encryption, okay? All right, so going back, I talked about how the rows are chained together, right? So the database is built into it a procedure to actually go back and just basically verify all the data to make sure they're properly chained together and has not been tampered with. Okay, so this is available within the database itself. Okay, and this is a good thing. Okay, so if you look at this, the first question you should ask yourself is, well, what is the database software that enforces immutability is bypassed, right? Because the thing that prevents you from updating the rows is the database. The thing that verifies the rows was the database, right? So what if someone actually, modified the database, right? Someone broke into Oracle headquarters, bribed a whole bunch of people, got some bad code slipped in, and so forth, right? Well, here's an example of what happens, right? So suppose the hacker changes the data beneath the Oracle database, right? So for instance, I inserted a record just said the price was 5 euros, right? So the hacker then went through, maybe they got access to the physical disk, right? And got super privileges at OS level, managed to override the block and make it look like an Oracle block and otherwise consistent and change the value. That's hard to do, but it's not impossible, right? Okay, now if you did that, okay, now you do a select, you can see the price has indeed been changed, right? So this hacker got beneath the database and they managed to change the database. And since the database was not involved in this, the database couldn't prevent that, right? Okay, so the bad thing happened. Now what happens is this. If you run the verify rows thing, you actually detect a signal saying, hey, something bad has happened. This row does not match, okay? And the reason it knows is because when you inserted the data, the new data, it changes the cryptographic digest of the row, right? Because the bits are different now. So the cryptographic digest changes, that means it no longer matches what's expected based on the following rows and so forth. Because remember, every single row after the current row has a cryptographic digest based on the initial row and so forth. Okay, so if you change it, the chains would no longer be consistent. And so we could detect this. Okay? So this is good. So we detect the fact that illicit tampering happened. And of course, given this database, we can always find the previous version of the row and restore the data. Okay? Now, in addition, it will tell you this failed and tell you, which is the data that's been modified, right? Okay, so at this point, the question to ask is, okay, fine. The verification function was run by the Oracle database. What if I don't trust the Oracle database to do the verification, right? Because if someone managed to defeat the Oracle controls, and then maybe they're smart enough to defeat that procedure too, right? Okay. That is why we actually released an open source version of the verification function, right? So the verification function is releasing source form, and then so what you can do is you can physically just read out the raw contents of the table, and then compute the checks, the cryptographic digest yourself independently, right? To show that indeed the data is correct, okay? And that's important, okay? That builds trust and transparency in this, right? And of course, the other property is that since these blockchain tables are tables fundamentally, they're very, very fast, right? Unlike conventional blockchains, these are just incredibly fast, right? And again, as you can see, it requires no application changes because it's only accessed via standard SQL, right? So you do insert, select, updates, and so forth, right? And in addition, since these are relational tables, you can do full analytics and transactions on the table data. Okay. All right. So I talked about various cases of hackers, insiders, and then cover-ups, right? So suppose you got a bad boss and just said, hey, I order you to do something bad and cover it up, right? So that, for instance, and this is an example of large-scale cover-up. So if you have access to all the data and you have the authority, in theory, you can just rewrite all the data, right, and recompute all the cryptographic digest and make it look okay, right? Who's to say that I didn't do that, right? An example, of course, order given by a corrupt executive or government authority to replace the database. Interesting, right? So the way to do this, detect this, is the following. As the cryptographic digests are computed, you can actually distribute them publicly, right? Because as they are computed, you just put them out there, right? And then put them in independent sources such that someone cannot come back later and say, gee, the cryptographic digest is now something else, because it's being published somewhere else already, right? The way to think about it is this way. If I just publish like a Twitter X feed, or even print in the New York Times, or just publish on Facebook, lots of different independent sources, right? Saying on such and such a date, on such and such a transaction date, my cryptographic digest is following, right? If I later changed the data, all the data and all the cryptographic digests, someone can go back and say, gee, that didn't match. This is what you said before, and this is what it is currently, and something has happened, right? So this is how you can detect this kind of massive cover-up, right? And the interesting thing about that, the cryptographic digest is a one-way computation. So given the cryptographic digest, you cannot figure out what the row contains. So it's privacy preserving, right? So that means it's safe to distribute anywhere, right? So I think the best practice is to post an independent public store. Like, for instance, Facebook is a good example, or just email it to a whole bunch of random strangers, right? Or actually, another interesting case is to publish these cryptographic digests periodically to a conventional distributed blockchain, right? Because conventional blockchains are also highly immutable, right? And you can also send them by email or by REST calls and so forth, right? Okay, so I think this is actually a very interesting case, right? Okay, see the time. Okay, so then see, these are all what ifs, right? You see, I don't trust. I think I will skip this case. I think because it's just actually. Let me see. I'm just sort of debating. Okay, that's okay. So this just says that, okay, prevent modification, right? So another threat you can think about is data falsification by impersonators. Because again, the question is, you trust the data, right? The question is, how do you trust the data, right? How do you know that the data in the tables have not been inserted by somebody who managed to steal somebody else's credentials and logged in as the other person, right? To prevent this kind of attack, we allow the end users to basically cryptographically sign the new data that they insert. Right? And so we assume that end users have public and private keys are certificates, right? And then each end user then, when they insert the row, they also sign cryptographically using their private keys, right? And then this way, we also store the public key, which is with the record, such that someone else can come back later and just use the public key to verify indeed the rows are correctly signed, right? So that indeed it was written by the person who claimed to be written, okay? And so forth. Okay. So what I've described is that it makes it easy to adopt blockchain technology because it's just standard SQL, right? And it can be used for financial data, logistics data, education data, because you don't want to forge, diplomas and so forth, government data, right? Legal data, tax documents, and corporate data. So it's actually very, very widely usable. Okay. Okay. So I'm going to switch to a related topic, which is actually very interesting, which is a more general topic, right? Notice how I talk about incorporating blockchain technology into a relational database, right? That is actually one example of an architectural approach, right? And this actually is not obvious, actually. It's not, because not everybody does it this way, right? Because for instance, there's actually two approaches right now. One is the Amazon approach. And the Amazon approach is important because Amazon has a very popular cloud service, right? And then their model is build and provide lots of single-purpose databases for each workload type. So a dedicated database type like Aurora for OLTP, a separate database type for key value stores, for documents, for in-memory, for time series, and so forth. So lots of different types, right? The Oracle approach, as you can see, we incorporate blockchain into our database is that we support using SQL to support multiple data types and workloads in a single database, right? And the reason this is important is because we see that modern apps require many different data types, right? So for instance, even a simple restaurant reservation application has relational data, talks about the properties of the restaurant, has text JSON documents, we're talking about user reviews and so forth, have map and graph data showing locations and so forth, and have graph data showing relationships among the people. Okay, so modern apps are much more complicated and use many different data types. And so you have dedicated databases like on the left-hand side, you have to move data among the different databases and manage all the different database types, right? Whereas with a single database that handles everything, it's a lot easier because data is always there, it's always consistent, right? And a good example is something like this. The tag that I like is to use a new capability, just add a SQL statement, not add a new database, right? So for example, with the movie example I gave, is that you can, in addition to the relational access pattern, you can look at the movie details as a JSON document and use JSON dot notation to access data, right? On the right-hand side is that, gee, if I rent this movie, I want to find out which of my friends also rent a similar movie. And that's like a relationship. Relationships are best modeled by graphs, who knows whom, right? And so that's a graph query, is that which customers are related to each other, rent the same movies, right? So on this side, I say, gee, well, maybe I want to do a vector search on this, which is using AI similarity search, right? Say, gee, find movies that are sort of similar to this movie, right? And notice how I just write a single SQL statement. I don't have to go out and install a separate vector database and learn separate vector database syntax to use this. I just use SQL syntax, right? And likewise, I use blockchain. I can protect this data and just making a blockchain keyword, and it just works. Okay, so this actually shows you the power of a converged database approach, where you're going to get average access to everything in a single database. Now, this is the analogy that I think is important to keep in mind, which is that think of your smartphone, right? In the old days, I did this myself, right? I had a phone, I had a GPS, I have a music player, I have a PDA for my calendar, right? They're all separate products, separate boxes you have to maintain, right? They've not converged in the features of smartphones. Every one of our smartphones have all this functionality, okay? The separate camera is obsolete. Actually, it's essentially obsolete, right? And this is why we think that new database technologies becoming features of the converged database, right? So like blockchain, I don't have a separate blockchain database. I just make blockchain a functionality of the converged database, right? And then it's simple to run and simple to develop than managing multiple separate products. And furthermore, the fact that they're converged enables new cross-feature innovations. So like on your phone, I can click on the map takes me to a location, the location gives me the information that I can link to other locations and so forth. So I can use it all together. I can cut and paste between different functionality without having to switch devices and so forth. Okay. Okay. So I talked about blockchain. I talked about the benefit of the converged database, right? But fundamentally, the way the blockchain works is the blockchain works with relational databases, right? And then, even though it's highly important, it's what if, someone says, what if I don't want to even use relational tables? Okay, yeah. And then, this is something that we've been working on, which is that we realize that JSON is highly popular with developers. It is, okay? But the relation is also very important. And so in some sense, these are sort of the strength of both, right? JSON is great because when the schema is evolving, right, it maximizes the developer productivity, and you store data as JSON documents, and you simple access them with, using get puts. Relational is great when the schema is known, and it maximizes data sharing because multiple data, you don't have to duplicate the data and so forth, right? And it's queryable and it's consistent, right? And so in the latest version of the Oracle database, we introduced something called the JSON relational duality, which allows you to allow the same set of data to be seen both relationally as well as via JSON. Okay? And the JSON object may actually consist of multiple relational tables, and we keep it all transaction consistent, such that if you modify the JSON object, the underlying relational tables are modified. If you modify the relational data, the JSON documents is modified. Okay? So this actually gives you the best of both worlds. So your application that wants to see the data as relational can just access conventional relational format. And if you want to expose it as a JSON document, you can do that also, and it's all consistently true. Okay. Okay. So I just want to summarize, and then there'll be one more slide. So blockchain database allows you to protect important data against list modification. Right? And we talk about basically bad actors, hackers, rogue insiders, as well as massive cover-ups. Right? And the key thing is that blockchain in the database makes it much easier, right? It's easily deployable with minimal application changes. As we've seen, SQL statements, right? And it becomes just a feature of the converged database, and you can use it in combination with other database features, right? And so we think that this really enables you to basically easily add blockchain integrity to database applications, right? And that's where your data is stored. Right? Okay. Okay, and this is my last slide, which is free, right? We've learned, that developers like free stuff, so we're making stuff free, right? And so we have Database 23 AI Free, which is the latest release with all the AI functionality, vector search, blockchain, and so forth, right? We have something called Live Labs, which allows you to actually run these things in an environment and test it and so forth, play with it, right? And then we have something called the AI Solution Hub that shows how to use the Oracle database with AI functionality for AI apps, right? And I think these are all very interesting. And the other thing I want to say about free is that giving something that's free for free is interesting, okay? But giving something that people charge money for free is actually much more interesting. Okay, so it's so this is something that we work really hard at, which is to give something that is of value, free, because we want to encourage adoption and try out new features. Okay, so that's basically it. Thank you. Okay. Okay. All right. Actually, I want to try something, which is something that I saw a speaker do, which is she did a groupie, which is a selfie with a group in the background. So I'm going to try that, see if that works, because I have never. Actually, this doesn't. Well, we'll see. Maybe, well, yeah, okay. This needs practice. Oh well, that's okay. It's a trial. So thank you very much. I hope you learned something from this. I think blockchain is cool. I actually think Oracle is cool. Okay, especially with other things that have changed. And I think the combination with all the AI stuff is going to cause a lot of great apps to be developed. So thank you. Okay. Yeah.